Okay, everyone, I'm going to go over the answers to the Simple Harmonic Motion Worksheet 1. I'll go over the second one with you next time. So the aim of this worksheet is to recognize and use these expressions that we learned for the position, the velocity, and the acceleration of something that is in simple harmonic motion. So our first question here is that an object oscillating with simple harmonic motion with a maximum displacement from the equilibrium position of 0.2 meters. We have a period of 0.1 seconds, and we have to find its speed when it is 0.06 meters from its equilibrium position. Okay, so the two equations we're going to use for this are that x of t is equal to a cos omega t, and we've got v of t is equal to negative a sine omega t. Sorry, negative omega a sine omega t. We have our period 0.1 seconds, our amplitude 0.2 meters, and we can figure out our angular velocity or angular frequency, they're the same thing, by 2 pi over the periods, and that comes out as 20 pi radians per second. Now, it's always more correct to leave it as pi's rather than taking the two decimal places, because pi is already an irrational number. So if we curtail pi to a couple of decimal places, it's not going to be as correct as if we just leave it in radian form, in pi form. So anyway, what we need to do first is we need to figure out what the time is going to be at 0.06 meters. So we use this equation here. We plug in 0.06 for x. We've got the amplitude 0.2 cosine omega t. That omega t is 0.06 over 0.2. And then we can use inverse cos to find out that this is going to be 1.27. All we do then is divide the time by omega, and we get 0.02 seconds. Now we can plug this 0.02 seconds immediately into our velocity, v of t. So we're going to have negative 20 pi radians per second times the amplitude times sine of 20 pi times 0.02. And that's going to give us a velocity of negative 11.95 meters per second. Now we're asked for the speed, so the speed is going to be the magnitude of the velocity, which is 11.95 meters per second. So let's just have a look at what's actually happening here. So here we have our box, and we've started it, because we're using a cosine graph, we started this at the maximum amplitude. Now I've chosen that we're going from left to right. So left to right is the positive direction, and right to left is the negative direction. So this is going to start here, and it's going to be going in this direction. So it starts at the positive maximum amplitude, so it's 0.2, and then it's going to move towards the equilibrium point of 0. So it's going to be moving to the left. So this comes down, and then it hits 0 here. That corresponds to the equilibrium position here. And then it's going to be moving towards the maximum negative amplitude. So that's why this part of the cosine graph is negative. So this part here corresponds to the maximum negative amplitude. And of course, after that, it's going to turn around and it's going to start going back, and it will hit the equilibrium point, and then eventually, at the end of the period, it will come back here to its original position. So that corresponds to up here. Now, if we look at what's happening with the velocity, so the velocity is going to be a negative sine graph of this. So we start the velocity in the same place as our graph here, but the difference is that at the maximum amplitude, the velocity is 0, because here it has to change its velocity from positive to negative or negative to positive. So it has to be 0 for a brief second before it changes direction. So that means at the maximum amplitude points, the velocity is always going to be 0. So then it's going to accelerate towards the equilibrium position, and it's going to reach a maximum velocity when it gets to this equilibrium position. So these points here correspond to the speed or the velocity at the equilibrium position. Now this is negative because we're moving to the left. So I've defined that as the negative direction. So we're going to move all the way through here to the left, and we're going to get to this point here, the maximum amplitude. That's going to be 0 velocity again because it has to turn around. And then we're going to increase our velocity in the positive direction until we get to here, the equilibrium point. And then we're going to keep going, and the velocity is going to decrease until it's back at its initial position after one period. Okay, so that is the relationship between the cosine graph for position and the velocity graph for the velocity. I should have said the sine graph for the velocity, sorry. Okay, so there's also an easy method for this. Now, you're going to hate me, but I didn't want to tell you this easy method because I wanted you to get used to these equations. So instead of doing all of this, we can just use one equation, and it's just this here. So we have v squared is equal to omega squared bracket r squared minus x squared close bracket. And if you just plug in the numbers here, that will give you the speed. It doesn't give you the sign of the velocity because this is a square, so it's always going to be positive. But it will still give you the speed, and usually the questions will ask you for the speed. And like I said, the reason I didn't give you this until now is because I wanted you to get familiar with using the equations above. Okay, so let's move on. So we have question 2. A mass is moving with simple harmonic motion. Displacement maximum is 1.1 meters. When t equals 0, its maximum speed is 0.33 meters per second. And we have to find its frequency and its speed after 2 seconds. So we have t equals 0. The maximum amplitude is 1.1 meters. We have velocity maximum of 0.33 meters per second. So remember that we can describe this as circular motion. So we can just use our circular motion equation here, that omega is equal to v over r. So r is going to be the amplitude, because if you had your circle, then your amplitude would be equal to the radius. So here we're going to use r as a max, as 1.1. So we just do that, and we have 0.3 radians per second for the angular velocity. Now we can also remember that angular velocity is 2 pi f, and then we can just rearrange this for f, and we get 4.8 times 10 to the negative 2 hertz. So that's fairly straightforward. Now we have to find its speed after 2 seconds. So we can just use our equation v of t is equal to negative a omega sine omega t. We just plug in omega that we found before, and we plug in the time. So it's going to be v of 2, and we get that velocity is negative 0.19 meters per second. Now I should have put that the speed would be the magnitude of the velocity, so it would just be 0.19 meters per second, but it doesn't really matter. I don't think you would get marks taken off you for that anyway. Okay, question 3. We have a spherical object performing simple harmonic motion between A and B. It appears stationary when viewed with a strobe light at 21 Hz and 28 Hz, but at no frequencies in between. So what you have to realize here is that when you use a strobe light to observe something in simple harmonic motion, if the strobe light has the same frequency or a multiple of that frequency as the simple harmonic motion, then the object is going to appear stationary. So all we have to do is figure out what is the common multiple of 21 Hz and 28 Hz, and of course that's going to be 7. So the frequency of this is going to be 7 Hz. So now we can work out the maximum speed. That's going to be using the equation that we discussed earlier, v equals omega r, this equation here. So v equals omega r, 2 pi f times r, and r again is the amplitude. So that's going to be 2 pi times 7 times 0.1, gives us 4.4 meters per second. So now we're also asked to find the acceleration. We can just use negative omega squared x for that. And straight away, we can tell that it's negative 77.4 meters per second squared, or 77.4 meters squared back towards the center or towards the equilibrium point. We also have to find the speed at point y. So y is 9 centimeters here. Sorry, I should have mentioned that x was 4 centimeters. I'm sure you got that. So y is 9 centimeters. So we can just plug that in here with omega and t. And we would get, first of all, we had for this method. So if you use the same method as I did before, where we use the inverse cosine, then you can find that the time is 0.061 seconds. And then we can plug that in here and we get 1.9 seconds. And again, if you want, you can use the easier methods, which is just this, that v squared equal to omega squared, r squared minus x squared, all brackets, and that will give us 1.9 meters per second as well. Okay, and that's here to say where the equilibrium points are on the position graph, and where the maximum displacement is. And this is about where y was. And I've added the turning points here, or the maximum amplitude points here on the velocity graph. And again, we have the equilibrium points where the velocity is plus or minus the maximum. Okay, so that's the first worksheet, and I'm going to upload the second one pretty soon.